Hello everyone, thank you for attending this talk. My name is Johannes. I'm a postdoctoral researcher at the University of Colorado Boulder, and this is collaborative research with the University of Southern California. So I'll speak about the large-scale extraction of historical land cover information from historical maps. In this talk I will briefly talk about topographic map processing in general and the recent advances in topographic map processing, and then I will talk about our processing pipeline for USGS historical topographic map collection, the HTMC, and then I'll briefly outline a few applications. Let's get started with topographic map processing. So topographic map processing is a interdisciplinary field that is based on computer science, based on geographic information science and cartography. As we all know, historical maps are unique witnesses of the past, and map processing focuses on the development of methods to extract and preserve geographic information contained in these historical maps. So basically converting agnostic color information into semantically informed geospatial vector data or raster data, and these data can then be used for retrospective landscape analyses. In particular, they can be used to extend retrospective analyses to the time period prior to remote sensing and prior to digital cartography, where generally spatial data is very, very sparse. Now recently we've witnessed an increasing availability of scanned and georeferenced historical map collections that are made available to the public. So what you can see to the right is an example of such a collection shown for Boulder, Colorado. So we see here the USGS historical topographic map collection, where you can nicely see how, of course, the city of Boulder has grown over time, but also how map layout, map design has changed, and how the map content has changed over time. So we speak about massive volumes of data, and the question is, how can we automate information extraction from such topographic map collections? In the case of the HTMC, all the maps are already stored on AWS S3, so we can make use of cloud-based data storage infrastructure. We can use advanced recognition and extraction models such as deep learning-based semantic segmentation and other supervised but also unsupervised classification methods. And we can use ancillary geospatial data to automate the sampling process. So, for example, to automate the training data generation process. Related efforts that people are working on are the development of methods for the automated georeferencing of maps, for the map content mining, and also for geometric corrections that can be applied automatically to maps, such as the alignment of historical maps to contemporary vector data. These are the recent trends in topographic map processing. Now I'll speak about the processing pipeline that we developed for the HTMC, for the USGS historical topographic map collection. So the HTMC consists of over 200,000 scanned and georeferenced topographic maps that date back to the 1880s of different scales. They are available as GeoTIFF and other data formats on AWS S3, and importantly, the HTMC comes with a very rich metadata as well. And what we can see here in this visualization is purely metadata based, so it basically shows the distributions of the maps at different scales and for different production years, so you can gain interesting insight into which map scales were used in which time period. Some of them have been discontinued and others are still used nowadays, such as the 24,000 map scale, and we're basically focusing on 24,000 and 62,500 in our work. Yeah, we can not only visualize this in the temporal domain, we can also visualize the map archive based on the metadata in a spatiotemporal progression. So you can nicely show here how basically the conterminous US have been mapped since 1885. So interesting patterns that can be seen here, but we can not only use the metadata for visualization, also actually conduct queries based on the metadata. For example, if we're interested in historical forest extents, we can query the earliest map per quadrangle that actually contains woodland tint, so in which the forests are depicted. We can also constrain this to specific map scales, and then based on the query result we can visualize the year in which the aerial image was acquired that underlies each historical map. So that was used for photo interpretation, and you can see interesting patterns in this map here. For example, you can see that the oldest maps containing forests are located in California, whereas others, such as these turquoise patterns here, are maps that are temporally referenced in more recent decades. Yeah, we can also, of course, do spatial queries if we're working on a specific geographic unit. Say we're interested in metropolitan areas and specific cities, so we can query maps for specific metro areas, of course. And these metadata-based queries are the core of our processing pipeline. So we start off with some metadata query. We download automatically the maps returned by that query from AWS S3. Based on the metadata, we also know the corner coordinates of each map, so we can automatically remove the map color, the map edge from the scanned map sheet. Now these downloaded geotiffs are of a very high spatial resolution, 1 to 5 meters, and that's too high for us, so we're interested in kind of lower resolutions here, and meaningful resolution. So what we do, we generalize the map to a meaningful resolution. Here, for example, we use an average of the RGB information in grid cells of 100 by 100 meters. We can then automatically mosaic these individual maps together and then ultimately perform some kind of analysis on the resulting maps, which I will show in a bit. So we are currently working on 3 different applications. One of them focuses on the extraction of historical forest areas. We've worked with historical urban areas where we actually combine remote sensing derived data, the global human settlement layer, with color information from historical maps to backdate urban areas. And we're working with historical road networks where we try to use historical maps to get an age estimate for each contemporarily existing road network segment, what you can see here. But for the sake of time, I'll just focus on historical forest areas in this talk. Yeah, historical forest extents as an exemplary application here of our processing pipeline. So the goal is to generate a conus-wide historical forest map. So what we did, we queried and downloaded the earliest map containing forests for each quadrant. From each of these map sheets. We've done this for over 50,000 map sheets, conus-wide. This is still work in progress, so I can only show the results for the western states. So this would be the extracted historical forests layer. But and this is important that, of course, this layer is temporally referenced in a very, very heterogeneous way, as you can see from this map, which we've seen before in this talk. So this is a fundamental difference to remote sensing data, where we can easily obtain a forest map for a specific season of a specific year, but if we use historical maps, we're obviously limited to the years in which maps were produced or updated. What we did, we compared these extracted forest areas to contemporary land fire forest cover classes or vegetation classes, which are derived from Landsat data, and we kind of cross-tabulate the areas of the historical forest that we extracted to the right and how they correspond to the vegetation classes from landfire. We can observe that most of our historical forest corresponds to contemporarily covered or tree cover or shrub cover or herb cover. So this seems to be promising, this seems to be logical, so this is promising for future work. And concludingly, I can say that the data storage and processing infrastructure enables large-scale information extraction from historical map collections. So it's possible to work with thousands and thousands of maps. It takes time, in particular the download, but it's doable. We've proposed a pipeline that is able to handle such large amounts of data. But important, if we work at large spatial extents rather than small areas, the information that we extract obviously will inherit the temporal heterogeneity from the source data, as we've just seen. However, we think that such extracted information is valuable and will potentially allow to calibrate long-term historical land use land cover models in order to make future projections of land use and land cover change more reliable, and ultimately to allow for a more informed decision making and regional planning. Thank you very much.